The James Webb Space Telescope isn't just showing us the past, it's rewriting it. By looking back 13.5 billion years, Webb has revealed a universe that wasn't calm or simple, but chaotic, violent, and alive with activity far earlier than anyone believed possible. What it found challenges everything we thought we knew about the birth of galaxies, black holes, and the very timeline of cosmic history. When we step back and think about how the universe was expected to unfold after the Big Bang, it's clear that scientists once believed in a relatively slow and orderly beginning. According to the standard cosmological model, the first few 100 million years following the Big Bang were a period of simplicity. Matter had only just cooled enough for hydrogen and helium atoms to form, and these primordial gases slowly began clumping together under the pull of gravity. The earliest structures were thought to be tiny, dwarfish galaxies, faint star clusters, and isolated pockets of light struggling to ignite in the vast dark. This period is often called cosmic dawn, when the first stars flickered on, bathing the universe in light for the first time since the afterglow of the Big Bang faded. The expectation was that galaxies, the grand cities of stars we see today, needed vast stretches of time to assemble. Models suggested that the earliest galaxies were mere fragments compared to the spirals and giant ellipticals we now observe across the universe. These fragments were expected to collide and merge slowly over billions of years, each merger contributing to the growth of larger and more complex structures. The process was envisioned as gradual and stepwise, like building a cathedral stone by stone. From the tiny star-forming halos at the dawn of time, through billions of years of accumulation, the galaxies we see in the nearby universe, majestic spirals like the Milky Way, were thought to be the end products of this patient cosmic construction. There was a certain comfort in this view. It painted the early cosmos as a calm nursery rather than a battlefield. The stars were young, the galaxies were small, and everything followed a kind of natural rhythm. In this picture, violence existed, but it was delayed. Large-scale collisions and complex structures would only appear after hundreds of millions, even billions, of years. The universe at first was to be a place of order, not chaos, where time was the main architect shaping galaxies into what they are today. This model wasn't just guesswork. It was built on decades of observations and simulations. Astronomers using earlier telescopes like Hubble and ground-based observatories could only peer so far back in time. What they saw seemed to confirm this idea. The further away they looked, the smaller and simpler the galaxies appeared. The faint smudges of light from billions of light years away looked like baby galaxies, tiny, irregular, and unstructured. They lacked the grandeur of later spirals or ellipticals, and that fit neatly into the model. It seemed to confirm that the cosmos was indeed slow in its growth, patiently assembling piece by piece. Cosmological simulations also reinforced this belief. Powerful computers modeled how gravity, dark matter, and gas should interact across billions of years. The results consistently showed that galaxies began as small halos, merging only gradually to form larger ones. In these simulations, the timeline of cosmic structure was orderly. Everything had a place, and everything took time. The idea that massive galaxies, or large-scale collisions, could exist just a few 100 million years after the Big Bang was almost unthinkable under this framework. Another layer of confidence came from what scientists knew about star and black hole formation. Stars, particularly massive ones, enrich their surroundings with heavier elements only after they die and explode. This takes time, meaning the earliest galaxies should have been poor in heavy elements, dim, and slow-growing. Similarly, black holes were expected to form from the remnants of early stars and grow steadily over billions of years. There simply wasn't supposed to be enough time for enormous black holes or vast galaxy clusters to emerge so early. In other words, the physics of growth seemed to demand patience. And so, for years, this was the dominant picture. A quiet dawn, followed by gradual growth, with the universe only becoming truly dramatic long after its beginning. The models made sense, the observations supported them, and the timeline felt consistent with the vast scales of cosmic history. To scientists, the early universe was supposed to be simple, predictable, and comprehensible. But then, the James Webb Space Telescope opened its golden mirrors to the sky, and with its unprecedented infrared vision, it began peeling back the veil of the earliest epochs. What it revealed was not the quiet nursery that had been imagined, but something entirely different. Instead of fragile beginnings, Webb captured a cosmos that was already roaring with activity, galaxies smashing together, black holes forming and colliding, and cosmic structures appearing far earlier than theory allowed. The contrast between expectation and reality was staggering. This is where the story turns. What scientists thought they would see, a calm, orderly rise of small galaxies into greatness, was shattered. Webb didn't just provide sharper images, it forced us to rethink the very foundations of cosmic history. If the early universe wasn't calm and slow, but violent and fast, then every model of galaxy formation, black hole growth, and cosmic evolution has to be questioned. The stage was set for a cosmic revelation, and Webb delivered it. Now we move from expectation to discovery, from the predicted calm to the observed chaos. What Webb actually saw in those first glimpses into the deep past reshaped everything we thought we knew. The early universe, far from being tranquil, turned out to be a place of collisions, mergers, and astonishing complexity, an untamed frontier that defies our understanding. When the James Webb Space Telescope first opened its eyes to the early cosmos, astronomers expected to confirm what decades of theory and simulation had prepared them for. Faint smudges of light, tiny galaxies in their infancy, fragile and scattered like sparks in a vast darkness. But instead, Webb revealed something entirely different, an early universe that was not calm at all, but shockingly alive with violent interactions. Just a few 100 million years after the Big Bang, at a time when galaxies were thought to be small and immature, Webb found enormous galactic structures already colliding, merging, and shaping one another in ways that seemed impossibly advanced for such an early age. The telescope's infrared vision, sharper and more powerful than anything that had come before, cut through veils of cosmic dust and gas to expose scenes of unimaginable chaos, vast mergers, gravitational entanglements, and galaxies assembling with a speed and scale that defied every expectation. The twist wasn't just that galaxies existed earlier than predicted. Hubble and other instruments had already hinted at early galaxies, but what Webb captured was their complexity and violence. Instead of a universe filled with quiet, isolated islands of stars, Webb's deep fields uncovered massive systems pulling together in dramatic, tangled webs. Some galaxies appeared surprisingly large, their stellar populations more developed than they should have been, given the short span of time since the Big Bang. Others showed signs of intense star formation and structural organization, as though they had skipped stages of gradual growth and jumped straight into advanced forms. This was more than just an observational surprise, it was a fundamental contradiction to the story scientists thought they knew. Perhaps most astonishing was the sheer scale of interactions. Webb detected galaxies in the process of colliding just a few 100 million years after the beginning of time. These weren't the slow, leisurely mergers models had predicted billions of years later. These were rapid, violent crashes happening when the cosmos was still in its infancy. The sight of massive galaxies smashing together so early was like finding skyscrapers in a village that was supposed to have only huts. How could such colossal systems exist, let alone collide, so soon after everything began? The evidence wasn't limited to a single instance. Across multiple fields of observation, Webb found repeating signs of galactic turbulence, tidal tails stretching out from galaxies ripped apart by gravitational forces, luminous bursts from furious star formation triggered by mergers, and compact groups of galaxies that seemed too developed for their age. Everywhere Webb looked, the story of the early universe was the same: raw, chaotic, and accelerating at a pace far beyond what the models had ever suggested. This left astronomers grappling with a profound question. Had they misunderstood the timeline entirely? If galaxies were already massive enough to undergo such violent interactions just a few 100 million years after the Big Bang, then the processes driving galaxy formation must have been far more efficient and far faster than anyone believed possible. It suggested that matter was collapsing into structure at a breakneck pace, as though the universe had skipped ahead in its own story. Instead of the patient unfolding scientists imagined, the cosmos looked like it had raced into complexity almost immediately. The shock of these observations reverberated through the scientific community. For decades, the consensus had been that complexity took time, that the grand spirals and giant ellipticals of the modern universe were the product of slow, deliberate growth. But Webb shattered that idea by showing that the seeds of such structures, and even their early collisions, were present almost from the beginning. This wasn't just a revision of detail, it was a rewriting of cosmic history. What Webb saw made it clear: the early universe was not the serene cradle scientists had expected. It was a storm, a maelstrom of galaxies interacting on scales no one thought possible so soon. The cosmic dawn was not gentle. It was violent, rapid, and filled with collisions that shaped the universe in ways we are only beginning to grasp. This revelation set the stage for even more astonishing discoveries, each one peeling back another layer of the mystery. If galaxies were already crashing into each other within the first billion years, what else was happening in that chaotic age? To answer that, we must turn to Webb's next revelation: the shocking discovery of chaotic mergers in the dawn of time, where entire groups of galaxies weren't just forming, but smashing together almost immediately after the Big Bang. The discoveries made by the James Webb Space Telescope did not just show that galaxies existed earlier than expected. They revealed that these galaxies were not quietly drifting through space, but were actively crashing into one another in complex, large-scale mergers almost immediately after cosmic dawn. This was one of the most shocking twists in modern cosmology, because mergers of this kind had always been considered late-stage events, reserved for a more mature universe billions of years old. Yet Webb has shown us that the very first act of cosmic history was not one of quiet growth, but of violent assembly. In the deep fields captured by Webb's golden mirrors, astronomers saw unmistakable signs of galactic collisions: elongated tidal tails stretching across millions of light-years, streams of stars torn from their host galaxies, and dense regions where multiple galaxies were packed together so tightly that interaction was inevitable. It was a universe in motion, turbulent and messy, and utterly unlike the calm nursery once imagined. To appreciate how surprising this is, we need to remember just how young the universe was at this point. Cosmic dawn, the period beginning roughly 200 million years after the Big Bang, marked the birth of the first stars and galaxies. According to older models, galaxies in this era should have been tiny, mere building blocks that had yet to mature into the grand structures we see today. These fragile systems weren't expected to have the mass, stability, or density required for large-scale collisions. They should have been separated by vast stretches of space, evolving in isolation before gradually coalescing over billions of years. Yet Webb has revealed a different reality. Galaxies so close together that mergers were happening almost immediately after they formed. This would be the equivalent of building a city overnight, only to watch skyscrapers topple into each other within hours. The images captured by Webb reveal not only that these galaxies were colliding, but that the collisions themselves were complex. We are not talking about simple two-galaxy interactions. Instead, Webb has observed multi-galaxy mergers involving 3, 4, or even more galaxies tangled together in cosmic chaos. These systems look like knots of light, glowing cores pressed against one another, surrounded by swirling streams of stars and gas that have been ripped free by gravity's relentless pull. Some of these interactions are so intricate that they resemble vast cosmic dances, with galaxies twisting and warping as they spiral toward one another. What is truly startling is how common such events appear to be. Webb's deep field observations suggest that these chaotic mergers were not rare exceptions, but frequent occurrences in the early universe. The physics behind these mergers only deepens the mystery. For such events to happen so early, galaxies must have formed with far greater mass and density than previously thought. The gravitational forces required to pull multiple galaxies into these collisions would have needed enormous amounts of matter concentrated in relatively small regions of space. This raises profound questions about the role of dark matter, the invisible scaffolding of the universe. Dark matter is thought to provide the gravitational framework upon which galaxies assemble, but Webb's observations suggest that this framework may have been far more efficient at pulling matter together than models predicted. If dark matter clumped faster or behaved differently in the early universe, it could explain how galaxies reached collision-ready sizes so quickly. Another striking feature of these mergers is their effect on star formation. When galaxies collide, their gas clouds are compressed, triggering bursts of starbirth known as starbursts. Webb's data shows galaxies in the early universe glowing with incredible intensity, likely due to such starburst activity. Some of these systems are producing stars at rates hundreds of times faster than the Milky Way does today. This furious pace of star formation would have rapidly transformed these galaxies, enriching them with heavier elements and shaping their evolution in ways no one expected so soon. Instead of gently building stars over billions of years, these galaxies seem to have exploded into life almost immediately after they formed. The implications of these chaotic mergers ripple out across our understanding of cosmic history. If galaxies were already colliding in complex groups within the first few 100 million years, it means that the timeline of structure formation is dramatically shorter than we thought. The universe wasn't slowly building its complexity, it was rushing headlong into it. This forces astronomers to reconsider everything from the growth of galaxies to the formation of black holes. After all, mergers are one of the main drivers of black hole feeding, and chaotic collisions would have provided ample fuel for black holes to grow rapidly. This could help explain why Webb also found evidence of unexpectedly massive black holes in the early universe. These revelations about chaotic mergers have set the stage for one of Webb's most dramatic discoveries: the observation of a multi-galaxy collision involving 5 separate galaxies, an event so early and so extreme that it defied every cosmological prediction. Nicknamed Webb's Quintet, this system embodies the chaos of the dawn universe and stands as a symbol of how radically our view of cosmic history has been upended. One of the most jaw-dropping discoveries made by the James Webb Space Telescope came in the form of a spectacle no one believed could exist so early: a 5-galaxy crash, a complex cosmic entanglement now often referred to as Webb's Quintet. This extraordinary system, observed only about 800 million years after the Big Bang, shows multiple galaxies colliding and merging simultaneously, a kind of gravitational traffic jam on a scale that defies all predictions. For decades, astronomers believed that groups of galaxies this large and interactions this extreme should not exist until much later, billions of years into the universe's development. And yet, there it was, glowing in Webb's infrared vision. 5 galaxies locked in a cosmic dance of destruction and creation at the very dawn of time. The idea of 5 galaxies crashing together so early is shocking for several reasons. First, galaxies themselves were not supposed to be massive enough to support such a collision in the first place. At 800 million years after the Big Bang, models predicted that galaxies should have been small, irregular, and widely spaced. The chance of finding even a 2-galaxy merger was considered rare at that stage, let alone a quintet. But Webb's images revealed distinct galactic cores, tidal bridges of stars stretching between them, and glowing streams of gas torn from their original hosts, all the signatures of an active, large-scale merger. It wasn't an illusion, and it wasn't a fluke. It was evidence of a universe far more dynamic than theory allowed. The structure of Webb's quintet is particularly fascinating. The galaxies aren't just aligned along our line of sight, as might happen in a cosmic coincidence. Instead, their interactions show they are genuinely gravitationally bound, tugging and pulling on each other in real time. Webb captured the faint tendrils of matter connecting them, like cosmic scars etched into the fabric of space. These features are only produced when galaxies pass close enough for their mutual gravity to rip stars, gas, and dust out of one another, weaving them into luminous bridges and chaotic spirals. The fact that such features exist proves beyond doubt that this quintet is not just a chance alignment, but a genuine multi-galaxy collision in progress. The implications of this are staggering. A 5-way merger accelerates every evolutionary process astronomers thought they understood. Collisions funnel vast amounts of gas toward galactic centers, fueling both starbursts and the rapid feeding of central black holes. In the case of Webb's quintet, the intense glow captured by the telescope suggests that star formation is occurring at breakneck speed, perhaps hundreds or even thousands of solar masses worth of stars being born every year. This means that galaxies involved in such an event could evolve into massive, complex systems incredibly quickly, skipping evolutionary steps that were once thought to take billions of years. Even more puzzling is what this says about black holes. Multi-galaxy mergers provide the perfect conditions for black holes to collide and grow, and Webb's quintet may have been a breeding ground for the earliest supermassive black holes in the universe. The sheer density of matter funneled inward during such a colossal merger would have provided enough fuel to transform small seed black holes into giants much faster than conventional models permit. This might help solve the mystery of how black holes billions of times the mass of our Sun managed to appear so soon after the Big Bang. But it also raises new questions about whether our understanding of black hole growth is fundamentally flawed. What makes Webb's quintet so extraordinary is not just that it exists, but that it suggests such events may not have been as rare as once believed. If Webb happened to capture one such colossal collision in its early surveys, it means the early universe could have been littered with similar systems. This paints a picture of cosmic dawn not as a time of quiet, scattered galaxies, but as an era of constant, large-scale interactions. Instead of drifting alone in the void, galaxies were packed so tightly together that collisions were inevitable, and quintet-like systems may have played a crucial role in rapidly shaping the universe into the large-scale structures we see today. Astronomers now view Webb's quintet as a direct challenge to the very timeline of cosmic history. If galaxies were already large, dense, and chaotic enough to produce 5-way crashes in less than 1 billion years, then the models predicting gradual growth over cosmic time must be re-examined. The quintet shows us that nature didn't wait billions of years to get complicated. It was complicated almost immediately. The discovery of Webb's quintet has become a symbol of the telescope's revolutionary power. It is more than just a beautiful image. It is a puzzle piece that doesn't fit into the current cosmic framework. It forces scientists to ask uncomfortable but necessary questions. How did matter clump together so quickly? What role did dark matter play in these early collisions? And most importantly, how many other such systems are waiting to be discovered just beyond our current view? The answers to those questions may reshape cosmology itself. But for now, Webb's Quintet stands as a breathtaking reminder that the universe's story is not one of patience and order, but of urgency and chaos. And it leads directly to the next great puzzle. Why such events are so strange, and why, by every rule of theory, they shouldn't exist at all. The discovery of colossal mergers like Webb's Quintet is not just visually stunning, it is profoundly unsettling for cosmologists, because by every expectation of astrophysical theory, galaxies that early were not supposed to be massive enough to collide on such a large scale. At just 800 million years after the Big Bang, the universe was still in its infancy. Matter had only recently cooled enough to form the first stars and primitive galaxies. According to long-standing models, these galaxies should have been small, faint, and fragile, little more than irregular clumps of gas and stars slowly finding their shape. Instead, Webb has revealed sprawling galactic systems crashing together as though they had skipped ahead by billions of years in their evolution. Why is this so strange? The answer lies in the timeline of growth. After the Big Bang, the universe began as a nearly uniform sea of hot plasma. Tiny fluctuations in density, seeded by quantum variations during inflation, grew slowly under the pull of gravity. Over hundreds of millions of years, these fluctuations became the first dark matter halos, the invisible scaffolding into which gas collapsed to form stars and galaxies. But this process, in theory, was gradual. To produce galaxies massive enough to undergo large-scale collisions, you would need enormous amounts of gas to condense and stars to form in vast numbers, something thought to require billions of years. And yet, Webb has shown that within just a few 100 million years, galaxies weren't only forming, they were already massive enough to collide with one another in dramatic fashion. Some of the galaxies involved in these early mergers are comparable in size to the Milky Way today, despite existing in a universe that should not yet have had the time to build them. This is like walking into a nursery and finding not infants, but fully grown adults. It defies the expected pace of development. The sheer mass of these early galaxies is particularly baffling. To create a system capable of colliding in a 5-galaxy crash, you need galaxies with billions, even trillions of stars. But the gas available at the time should not have been dense enough to create such massive systems so quickly. The models predicted dwarf galaxies forming first, then slowly merging into larger structures. Instead, Webb is showing us giant galaxies already present and already interacting, suggesting either that our models underestimate the speed of galaxy formation or that some unknown mechanism accelerated the process. Dark matter is one possible explanation, but even here, the puzzle deepens. Dark matter halos provide the gravitational wells that pull ordinary matter into galaxies. If these halos clumped faster than predicted, they could have accelerated galaxy formation. But the degree of acceleration required to explain Webb's findings is staggering. It would mean that our entire understanding of dark matter's role in cosmic evolution needs to be reconsidered. Did dark matter behave differently in the early universe? Was there some property of it we have not yet discovered that allowed structures to form at hyperspeed? These are now open questions, sparked directly by Webb's strange observations. Another bizarre consequence is what this means for star formation. For galaxies to become massive so early, they must have been forming stars at extreme rates, far beyond anything seen in the modern universe. In fact, Webb has already confirmed galaxies with starburst activity producing hundreds of solar masses worth of stars every year, compared to just a handful in the Milky Way today. But this level of activity also raises contradictions. Starbursts consume gas rapidly, which should limit long-term growth. So how did these galaxies not only survive, but also grow large enough to crash into each other in such enormous numbers? Something in the physics of early star formation may be missing from our current models. The strangeness doesn't end there. Collisions on this scale were also expected to be rare in the early universe, because galaxies were thought to be spread farther apart. While the universe was denser overall, the galaxies themselves should have been too small to make collisions of this magnitude commonplace. And yet Webb has found not just one example, but repeated evidence of large-scale interactions. This implies that the universe at dawn was far more interconnected and dynamic than we realized, a tightly woven web of matter where galaxies were practically born into conflict. This all adds up to a profound tension between observation and theory. If galaxies this young were already colliding, then the assumptions behind our cosmological timeline may be deeply flawed. The rules we thought governed the pace of structure formation, the rate of gas cooling, the role of dark matter, the build-up of stars and black holes, may not apply to the early universe in the way we believed. Instead of a calm unfolding, the cosmos seems to have burst into complexity almost immediately, skipping the intermediate steps that were supposed to define its growth. And this is what makes Webb's findings so strange. They don't just add detail to the cosmic story, they break the story entirely. They reveal a universe that is older in behavior than in age, a cosmos whose infancy looks suspiciously like maturity. This forces scientists to ask whether the very timeline of the Big Bang model is correct, or whether something fundamental is missing in our understanding of how the universe evolved. From this unsettling contradiction emerges another revelation. Webb hasn't just seen galaxies colliding, it has also detected black holes merging incredibly early, a discovery that adds even more fuel to the mystery of how cosmic structures could grow so massive so fast. Among the most astonishing revelations from the James Webb Space Telescope is the discovery that black holes were already colliding and merging as early as 740 million years after the Big Bang. To put that into perspective, this is less than 1 billion years into the universe's 13.8 billion year history, barely the opening act of cosmic time. For decades, astronomers assumed that black holes, particularly the supermassive ones that sit at the centers of galaxies, required billions of years to grow. They were thought to begin as small remnants of massive stars, then gradually feed on gas, dust, and stars to increase their size. But Webb has revealed that this picture is far too slow. Instead, the early universe was a stage of rapid black hole assembly, with mergers happening in what should have been the cosmic dawn. The evidence for this comes from Webb's unparalleled ability to peer through dust and gas using infrared light. Hidden at the centers of young galaxies, Webb has detected active galactic nuclei, bright signatures of supermassive black holes consuming matter at incredible rates. But even more surprising, it has observed pairs of black holes caught in the act of merging. These detections are not just suggestive. They provide hard proof that massive black holes were already colliding in the earliest epochs of galaxy formation. This means the seeds of these black holes must have been much larger than previously imagined, or that they were able to grow at breakneck speeds. Either way, this discovery upends one of the most fundamental assumptions in astrophysics. The strangeness of these early mergers lies in the timeline of growth. For a black hole to reach millions or billions of solar masses by just 740 million years after the Big Bang, it would have had to grow far faster than accretion models allow. The Eddington limit, a theoretical cap on how quickly black holes can grow by feeding on matter, makes it nearly impossible for such enormous black holes to grow holes to form in under 1 billion years. Yet Webb's discoveries imply that these limits may either have been bypassed or were not as strict in the conditions of the early universe. Some astronomers now speculate that direct collapse black holes, giant black holes that formed directly from collapsing gas clouds without ever being stars, might explain how these monsters appeared so early. If true, it would mean that the early cosmos had pathways for black hole formation that do not exist today. The mergers themselves are equally fascinating. When two galaxies collide, their central black holes are pulled toward one another, eventually spiraling in and merging into a single, larger black hole. Webb's observations of early galactic mergers show that this process was already happening in the first billion years. These collisions would have been some of the most violent events in the universe, releasing energy in the form of gravitational waves, ripples in space-time that spread across the cosmos. Although Webb cannot directly detect gravitational waves, its observations align with the idea that the early universe was alive with such signals, many of which are now being sought by detectors like LIGO and Virgo. In fact, Webb's discoveries suggest that the early universe may have been far louder in gravitational waves than previously thought. The consequences of these early mergers extend far beyond black hole growth. When black holes collide, they can shape the galaxies around them, heating gas, driving outflows, and regulating star formation. In the case of the early universe, this means that galaxies may have been shaped by black holes much earlier than expected. Instead of being passive passengers in galactic evolution, black holes were active engines, carving out their environments and influencing how galaxies grew. This blurs the line between which came first, the galaxy or the black hole, and suggests that their growth has been deeply intertwined from the very beginning. Even more perplexing is the sheer number of massive black holes Webb has uncovered at high redshifts, the measure of how far back in time we are looking. These aren't just a few anomalies. They are numerous enough to suggest that rapid black hole growth was a common feature of the early universe. This abundance challenges the standard model of cosmology, which predicts far fewer massive black holes at such early times. It raises the question, did we underestimate the efficiency of black hole growth? Or is our timeline of cosmic history fundamentally flawed? Some researchers have proposed exotic possibilities to explain these findings. Could dark matter have played a role, accelerating the collapse of gas into black holes? Could new physics, beyond what we currently know, have allowed black holes to bypass growth limits? Or perhaps our assumptions about the conditions of the early universe, its density, temperature, and structure, are incomplete. Webb's detection of these early mergers is not just a surprising discovery. It is a challenge to the very laws we thought governed the cosmos. What is clear is that the early universe was far from the quiet, orderly place once imagined. It was a violent frontier where galaxies smashed together and black holes collided in a frenzy of growth. This raw, untamed universe reshapes our understanding of how cosmic structures formed and forces us to rethink the timeline of everything, from galaxy evolution to the role of dark matter and dark energy. And that brings us to the next crucial piece of the puzzle. If black holes and galaxies were growing so fast, what does this say about galaxy formation itself? Webb's discoveries demand a new look at how galaxies formed, how quickly they assembled, and how these chaotic processes redefined the universe's earliest history. The James Webb Space Telescope's revelations about early collisions and black hole mergers carry seismic implications for our understanding of galaxy formation. For decades, cosmology has been anchored by the belief that galaxies are the product of slow, steady evolution. They were thought to begin as faint, irregular clumps of stars, gradually merging and accreting material across billions of years, until they became the majestic spirals and ellipticals we see in today's universe. But Webb's observations paint a very different picture. Galaxies were not creeping toward complexity, they were racing into it. This forces us to confront the idea that galaxy formation, growth, and merging all happened on timescales much shorter than models had ever suggested. At the heart of this paradigm shift is speed. The fact that Webb detected massive, interacting galaxies just a few 100 million years after the Big Bang suggests that the processes driving galaxy growth were extremely efficient. Gas clouds must have collapsed into stars at blistering rates, far beyond the pace we see in the modern universe. Starburst activity, where galaxies form stars hundreds of times faster than the Milky Way, appears to have been the norm rather than the exception in this early epoch. This hyperactive growth would have allowed galaxies to gain size and mass quickly, making them ready to collide and merge long before theory said they should. Instead of billions of years, it may have taken only hundreds of millions for galaxies to leap into maturity. This accelerated pace challenges the core assumptions of cosmological simulations. Current models rely on parameters like gas cooling rates, dark matter halo growth, and star formation efficiency, all of which were tuned to match the slower timelines implied by earlier observations. But Webb has shown that those parameters may not apply to the early universe. Cooling may have been more efficient, dark matter may have clumped more quickly, or some unknown mechanism may have turbocharged star formation. Whatever the explanation, the implication is clear. Galaxies were building themselves at a speed our models cannot yet replicate. Mergers, too, appear to have played a much bigger role than anticipated. Webb's detection of multi-galaxy collisions, including the dramatic Quintet, suggests that mergers weren't rare events reserved for later epochs. They were central to the universe's early story. In fact, mergers may have been the dominant mode of galaxy growth at the dawn of time. Rather than assembling gradually, galaxies may have been born into crowded neighborhoods where collisions were inevitable. These mergers would have rapidly reshaped galaxies, triggering intense starbursts, fueling black hole growth, and creating massive systems in record time. It wasn't the slow stitching together of a cosmic quilt. It was a wild, chaotic weave, with entire galaxies thrown together at once. One particularly striking implication of this is that galaxies may have reached large sizes much earlier than expected. Some of the systems Webb has observed are already comparable in mass to the Milky Way, even though they existed less than 1 billion years after the Big Bang. This is almost impossible to reconcile with older models, which predicted such massive galaxies would require billions of years of accumulation. If galaxies could grow this large so fast, it means the universe's structure took shape on a timescale dramatically shorter than we believed. The role of black holes in this accelerated formation cannot be ignored. As Webb revealed, black holes were already merging and growing at astonishing rates in this era. Their influence on surrounding galaxies, through gravitational pull, radiation, and energy outflows, would have shaped galaxy growth in profound ways. In the modern universe, we see black holes regulate star formation by blowing gas out of galaxies. But in the early universe, their rapid growth during chaotic mergers may have fueled galaxy assembly, pumping energy into their surroundings and accelerating the birth of stars. This symbiotic relationship between galaxies and their central black holes appears to have been established almost immediately, not billions of years later as once assumed. These discoveries also reshape how we think about cosmic structure. If galaxies formed and merged faster, then clusters and filaments, the vast webs of interconnected galaxies stretching across the universe, must also have emerged earlier than models predict. Webb has indeed found hints of these structures at high redshifts, showing that the large-scale scaffolding of the universe was already in place long before we thought possible. This suggests that the universe wasted no time in organizing itself into the grand cosmic web that defines its structure today. All of this raises a profound question. Have we underestimated the efficiency of the universe itself? Perhaps the conditions of the early cosmos, its density, temperature, and distribution of matter, were far more conducive to rapid galaxy formation than we realized. Or perhaps there are elements missing from our models altogether, such as new physics governing dark matter or previously unknown processes in star and black hole growth. Whatever the answer, Webb's discoveries force us to rethink the very foundations of galaxy formation theory. The implications extend beyond astrophysics into cosmology as a whole. If galaxies were forming, merging, and evolving faster than expected, then the timeline of the Big Bang model itself may need revision. The cosmic clock we use to measure the universe's growth may not be ticking the way we thought. This opens the door to bold new interpretations, not only about galaxies, but about the fundamental forces shaping the cosmos. One of the deepest and most unsettling puzzles sharpened by the James Webb Space Telescope's discoveries is the mystery of supermassive black holes forming so early. Webb has detected quasars, galaxies with extraordinarily bright centers powered by actively feeding black holes, at times less than 1 billion years after the Big Bang. Some of these black holes are already billions of times the mass of the Sun, rivaling the giants at the centers of mature galaxies like the Milky Way. The problem is that according to all known physics, these monsters simply shouldn't exist yet. Black holes were supposed to start small, born from the deaths of massive stars, and then grow slowly over billions of years by consuming gas, stars, and merging with other black holes. Yet Webb shows us that in less than 1 billion years, the universe had already produced some of its most extreme objects. This revelation is more than surprising. It's a fundamental challenge to our understanding of cosmic evolution. To grasp why this is so baffling, we need to understand the growth limits black holes face. As matter falls into a black hole, it heats up and emits radiation, and that radiation pushes outward against the infalling gas. This balance, known as the Eddington limit, acts as a natural brake, preventing black holes from growing too quickly. Even if a black hole were to feed continuously at this maximum rate, starting from the collapse of the first stars, it shouldn't have been able to reach billions of solar masses in under 1 billion years. And yet, Webb is finding black holes that massive in galaxies that existed only 700 to 900 million years after the Big Bang. This implies that either black holes were somehow breaking the Eddington limit in the early universe, or that they were born far larger than we ever anticipated. One hypothesis gaining traction is the existence of direct collapse black holes. Instead of forming from dying stars, these would have emerged directly from the collapse of enormous gas clouds in the early universe, skipping the star stage entirely. Such black holes could begin their lives with masses of 10,000 to 100,000 suns, giving them a head start in the cosmic growth race. If conditions in the early cosmos, such as higher densities of pristine gas and the influence of dark matter, allowed such collapses to occur frequently, then the seeds of today's supermassive black holes may have formed almost instantaneously after cosmic dawn. Webb's discoveries lend credibility to this idea, but they also raise new questions. Why would direct collapse be so common early on, and why do we not see it happening today? Another possibility is that black holes in the early universe were growing through rapid mergers. Webb has already shown that galaxies were colliding at a furious pace during cosmic dawn. Every galactic merger would have brought central black holes closer together, eventually forcing them to collide and merge as well. These mergers would create larger black holes in leaps rather than gradual steps, bypassing the slow feed of accretion. If this process was widespread, it could explain how supermassive black holes appeared so quickly. But even this scenario has limits. The sheer number of massive black holes Webb is uncovering suggests that something more than just mergers was at work. A more radical idea is that our assumptions about physics itself may be incomplete. Perhaps black holes could accrete matter in ways we do not fully understand under the extreme conditions of the early universe. For example, super Eddington accretion could have allowed them to devour gas at rates far beyond what current theory allows. In this picture, the early universe was an environment so dense and turbulent that black holes could gorge themselves unchecked, growing by factors of thousands in just a few 100 million years. If true, it would mean that the physics of black hole growth is not universal but dependent on cosmic context. The presence of these massive black holes so early also complicates our view of galaxy evolution. Black holes and galaxies appear to grow together, influencing one another through feedback processes. If black holes were already massive within the first billion years, then they must have played a dominant role in shaping their host galaxies from the very beginning. Their immense gravitational pull would have funneled gas inward, driving intense starbursts, while their outflows and jets could have carved the surrounding environment. In other words, instead of galaxies slowly nurturing black holes at their centers, the black holes may have been the engines driving galaxy growth from the start. What makes this mystery so profound is its scale. These are not rare anomalies. Webb has already found multiple supermassive black holes at early epochs, and more continue to be discovered. Their very abundance suggests that our models of cosmic growth are incomplete. The impossible black holes Webb has revealed are not exceptions. They may have been the rule. And if that is the case, then the history of the universe needs rewriting. This leads us naturally into the next revelation: the surprising fact that interconnected structures, webs, and clusters of galaxies were also emerging far earlier than predicted. If massive black holes and galaxies were forming so quickly, then the cosmic scaffolding that links them together must also have taken shape much sooner than our theories allow. The James Webb Space Telescope has not only shown us that galaxies and black holes were growing at astonishing speeds, it has also revealed that the larger structures tying them together were already beginning to emerge far earlier than anyone thought possible. Instead of finding a universe filled with isolated, scattered galaxies, Webb has uncovered evidence of galaxies gathering into webs and clusters within the first billion years after the Big Bang. This is startling because cosmic structure on such a scale, the vast filaments and knots of the cosmic web that define today's universe, was expected to take billions of years to fully develop. Yet Webb's observations show that the universe's grand architecture was already visible in its earliest chapters. Clusters of galaxies are among the most massive structures in the cosmos, typically forming through the gradual gravitational pull of smaller groups, merging over vast stretches of time. According to previous models, the first protoclusters, early versions of galaxy clusters, should only have appeared well after a billion years. But Webb has detected protoclusters at redshifts corresponding to less than a billion years post-Big Bang. These collections of galaxies are not randomly scattered. They are gravitationally bound and showing signs of interaction, suggesting that the cosmic web was weaving itself together almost immediately after galaxies began to shine. What's particularly intriguing about these findings is the scale of organization. Webb has identified chains of galaxies aligned along filaments of matter, stretching across tens of millions of light years, at epochs when such coherence was thought to be impossible. The cosmic web, a vast three-dimensional network of filaments and voids shaped by the influence of dark matter, was believed to require billions of years to fully emerge. Yet here it is, already etched into the fabric of the early universe. This suggests that the seeds of cosmic structure must have grown far faster or under different physical conditions than models accounted for. Dark matter once again enters the conversation. These large-scale structures depend heavily on the behavior of dark matter, which provides the invisible scaffolding upon which galaxies cluster. If webs and clusters were already forming at such early times, it may mean that dark matter clumped together more efficiently in the aftermath of the Big Bang than scientists had predicted. Perhaps the density of dark matter in the early cosmos created gravitational wells so deep that galaxies could gather into large-scale structures with remarkable speed. Alternatively, our understanding of how dark matter interacts with itself or with normal matter may be incomplete, leaving room for unknown physics that accelerated the formation of structure. The discovery of early interconnected systems also raises questions about the timeline of cosmic rayonization, the process by which the first stars and galaxies ionized the hydrogen gas filling the universe, allowing light to travel freely. If galaxies were already clustered and forming stars at extreme rates, then reionization may have proceeded more quickly and more unevenly than previously thought, with clustered regions lighting up the universe in patches while other areas lagged behind. This paints a picture of the early cosmos not as a uniform sea of faint galaxies, but as a lumpy, interconnected landscape where some regions raced ahead of others in complexity. Another layer of mystery comes from how these structures may have influenced the rapid growth of galaxies and black holes themselves. Being part of a cluster or filament provides galaxies with more opportunities to collide, merge, and exchange material. In other words, the very existence of early interconnected webs may explain why galaxies and black holes were able to grow so quickly. They were not evolving in isolation, but within dense, dynamic environments where interactions were constant. This feedback loop of clustering, collision, and accelerated growth may be the key to understanding the unexpected maturity of the early universe. What is so remarkable is how these discoveries reshape our sense of time. For decades, we assumed that the universe needed billions of years to build its scaffolding, that the vast architecture we see today was the product of long, patient evolution. Webb has overturned this vision by showing us that the bones of the cosmic web were already in place within the first billion years. It's as if the universe skipped straight to advanced construction, laying out its framework with astonishing speed. This realization forces us to re-examine our timeline of cosmic history. If galaxies, black holes, and cosmic structures were all forming and growing far faster than expected, then the standard chronology of the Big Bang may not be telling the full story. The question becomes, do we need to rewrite the sequence of events in the early universe? If the universe was already home to large galaxies, massive black holes, and even complex structures like clusters within the first billion years, then the timeline we've relied on for decades is no longer sufficient. The James Webb Space Telescope has revealed that cosmic evolution was not the slow, patient process that models described. It was explosive, rapid, and chaotic. This forces us to ask, is our entire sequence of cosmic history misaligned? Did galaxies, stars, and black holes evolve on a compressed timescale that challenges the very framework of the Big Bang model? One of the biggest challenges lies in reconciling Webb's findings with the rate of cosmic growth predicted by the lambda cold dark matter model, the standard cosmological model built on dark matter and dark energy. According to lambda cold dark matter model, small fluctuations in the density of the early universe should have grown gradually under gravity, taking billions of years to create the large galaxies and black holes we know today. But Webb is showing us that these features were already in place within a few 100 million years. If galaxies were already enormous and interconnected at redshifts above 10, then something about the way we model growth is incomplete. Either the universe built itself faster than lambda cold dark matter model allows, or we are missing some fundamental mechanism that turbocharged early evolution. Another tension arises with supermassive black holes. As mentioned earlier, their growth should have been limited by the Eddington rate, which sets a cap on how fast they can consume matter. Yet Webb is detecting billion solar mass black holes in epochs where they shouldn't exist. If our timeline of black hole growth is wrong, it could mean that either black holes were seeded much larger than previously thought, through processes like direct collapse, or that they were growing in ways that defy the physics we currently know. Either explanation would require rewriting the sequence of cosmic events, pushing back the appearance of extreme objects to much earlier than the standard timeline allows. Star formation is also at the center of this puzzle. For galaxies to become so large so quickly, stars had to form at astonishing rates, far faster than in the modern universe. This suggests that early star formation was not just more common, but fundamentally different. Gas may have cooled and condensed into stars with remarkable efficiency, perhaps due to the higher density and pristine conditions of the early cosmos. If so, then our models of how quickly stars form need to be recalibrated. The cosmic clock we use to measure the growth of galaxies may be ticking at a pace that doesn't match reality. The presence of interconnected structures in the early universe adds yet another layer of complexity. The cosmic web, according to theory, takes billions of years to assemble into the vast filaments and voids we observe today. Yet Webb has revealed that even within the first billion years, galaxies were already clustering along filaments, forming webs of matter that look eerily similar to the modern universe on smaller scales. This suggests that the scaffolding of the cosmos was laid out with astonishing speed, raising questions about whether dark matter aggregated differently than we thought. If dark matter clumped more quickly, it could have accelerated the timeline, but that would also mean our simulations of structure formation need to be rethought from the ground up. Perhaps most unsettling is what these discoveries imply about the Big Bang model itself. While Webb's findings don't invalidate the Big Bang, the evidence for the universe's hot, dense origin remains overwhelming. They do suggest that our interpretation of what happened after may be flawed. The standard picture of gradual development may need to be replaced with one that accounts for much faster, more violent processes. Some researchers have even proposed that cosmic inflation or early dark matter dynamics might need to be reconsidered. Could it be that the early universe was governed by physical laws or interactions we haven't yet uncovered? Webb has forced us to keep this possibility on the table. Another possibility is that the universe's timeline of reionization, the era when the first stars and galaxies reionized hydrogen and made the universe transparent to light, occurred far earlier and more rapidly than expected. If galaxies were already massive and forming stars in clusters, then reionization may have been well underway by the time the universe was only a few 100 million years old. This, too, requires adjusting the cosmic clock, because reionization was supposed to take hundreds of millions of years more to unfold. All of these threads point toward a profound conclusion. The story of the universe's early growth has been underestimated, compressed into a timescale too slow to match reality. The evidence Webb has provided is not just a minor adjustment, it's a demand to rethink the sequence of cosmic events entirely. Galaxies, black holes, and large-scale structures did not patiently wait billions of years to evolve. They burst into existence far sooner, reshaping our understanding of what early really means. This kind of radical revision is both thrilling and daunting. On one hand, it opens new doors for discovery, forcing us to explore physics we may never have considered. On the other, it challenges the comforting clarity of the models we've relied on for decades. The universe, it seems, is not just stranger than we imagined. It's faster, more dynamic, and more unpredictable. And when we imagine galaxies forming and colliding so quickly, another picture emerges: a cosmos filled with galactic traffic jams, where the density of the young universe made collisions not just possible, but inevitable. When the James Webb Space Telescope turned its gaze toward the earliest epochs of the cosmos, one of the clearest patterns it revealed was that galaxies were not drifting peacefully apart. They were colliding with shocking frequency. These weren't rare, chance encounters, but common events, almost inevitable in a universe that was far denser than it is today. The early cosmos was smaller, more compact, and packed with matter that hadn't yet expanded into the vast emptiness we see now. Galaxies were born into neighborhoods that left them little room to breathe, and the result was what scientists now call galactic traffic jams, environments where collisions and mergers were not just likely, but routine. Yet even with this understanding of density, the scale and speed of these crashes still left astronomers astonished. To understand why collisions were so common, we need to step back and consider how the universe has expanded over time. Today, galaxies are separated by millions of light-years of mostly empty space, with collisions occurring rarely on cosmic timescales. The Milky Way, for instance, is expected to collide with Andromeda in about 4 billion years, a long wait by any standard. But rewind to less than 1 billion years after the Big Bang, and the picture changes dramatically. The universe was only a fraction of its current size, and galaxies were huddled together much more tightly. Their relative motions, driven by the gravitational pull of surrounding dark matter halos, meant that close encounters happened far more often. Simply put, the early universe was too crowded to avoid frequent crashes. Even so, the expectation among cosmologists was that early galaxies were small and fragile, producing mergers that were modest in scale. What Webb revealed instead were enormous systems colliding head-on, involving galaxies that were already surprisingly massive and complex. These weren't just star clusters brushing against one another. They were sprawling, luminous galaxies, smashing together in events that reshaped them entirely. The speed at which this was happening stunned astronomers. Mergers that were thought to require billions of years to produce seemed to have unfolded in a fraction of that time, leaving behind remnants that looked like galaxies far older than their true age. The fingerprints of these galactic traffic jams are everywhere in Webb's images. We see elongated tidal tails, streams of stars flung into intergalactic space by gravitational interactions. We see distorted galactic cores, stretched and twisted by the force of collisions. And we see bursts of light where collisions compressed vast clouds of gas, triggering the rapid birth of stars. These features are not subtle. They are dramatic, unmistakable evidence that galaxies in the early universe were constantly smashing into one another, creating new shapes and structures in the process. What makes this even more surprising is the diversity of the interactions Webb has uncovered. Some collisions involve just two galaxies, spiraling inward like dance partners locked in gravity's embrace. Others are far more chaotic, with 3, 4, or even 5 galaxies converging in the same region of space. These multi-galaxy collisions are particularly stunning because they require not only dense environments, but also significant gravitational coordination. For so many galaxies to be crashing together so early suggests that they were forming in tight clusters, bound by dark matter halos that were far more mature than expected for such an early epoch. The consequences of these traffic jams were profound. When galaxies collide, they don't simply bounce off one another like billiard balls. Instead, their stars and gas clouds are stirred, reshuffled, and often driven inward toward their galactic centers. This inflow of material fuels starburst activity, brief but intense periods where new stars are born at staggering rates. Some galaxies observed by Webb appear to be producing hundreds, even thousands, of new stars per year, compared to just 1 or 2 in the Milky Way today. These bursts of creation transformed young galaxies almost overnight, giving them a maturity and luminosity that defied their age. At the same time, galactic collisions funneled gas directly into the waiting mouths of central black holes. This process not only accelerated black hole growth, but may also explain why Webb found supermassive black holes so early in cosmic history. In a universe crowded with galactic traffic, black holes had a steady supply of fuel, allowing them to balloon in size at incredible rates. In this sense, the galactic traffic jams were not just shaping galaxies, they were shaping the evolution of the entire cosmos. The sheer speed of transformation is perhaps the most startling aspect of all. Collisions that should have required billions of years appeared to complete themselves in just a few 100 million. Galaxies that should have looked primitive instead looked surprisingly advanced, with organized structures and enriched stellar populations. This rapid evolution compresses the cosmic timeline, raising the question of whether our models have underestimated the efficiency of mergers in driving growth. Did galaxies evolve faster simply because they were colliding more often? Or is there some hidden ingredient, perhaps related to dark matter or early cosmic conditions, that supercharged the process? It is also worth noting that these galactic traffic jams were not rare exceptions. Webb's deep field surveys, which examine tiny slices of the sky, consistently reveal such collisions, suggesting that they were the rule rather than the exception in the early universe. If this is true, then the picture of a calm, slowly unfolding cosmos must be abandoned in favor of one that was crowded, chaotic, and in constant motion. The early universe was less like a quiet nursery and more like a bustling city intersection at rush hour, where collisions were bound to occur. For astronomers, these findings are both exhilarating and daunting. On the one hand, they provide a vivid explanation for how galaxies and black holes could grow so quickly. On the other, they challenge the assumptions baked into decades of cosmological modeling. The universe, it seems, was not patient in its youth. It was reckless, rushing headlong into complexity at a pace that continues to surprise us. And while these galactic traffic jams are fascinating in themselves, what makes them even more remarkable is that we can see them at all. It is only because of Webb's extraordinary infrared precision that these scenes of cosmic chaos have come into view. Where earlier telescopes saw only faint smudges of light, Webb sees detail: the twisted arms, the luminous cores, the faint bridges of stars linking colliding systems. This level of clarity has allowed astronomers to witness the violence of the early universe directly, capturing the very processes that rewrote the timeline of cosmic history. The discoveries that have so dramatically reshaped our picture of the early cosmos would not have been possible without the unprecedented precision of the James Webb Space Telescope. What makes Webb so revolutionary is not just its size or its location in space. It is the fact that it was designed specifically to observe the universe in infrared light. This capability allows it to pierce through cosmic dust, detect the faintest glimmers of ancient starlight, and stretch our sightline back to within a few 100 million years of the Big Bang. Where previous telescopes like Hubble could see the outlines of distant galaxies as dim smudges, Webb can now resolve those smudges into detailed structures, exposing the chaos of galactic mergers and interactions in ways that were unimaginable even a decade ago. Infrared vision is essential because of the way light behaves across cosmic distances. The universe is expanding, and as light travels billions of years to reach us, it becomes stretched, or redshifted, into longer wavelengths. The earliest galaxies are so distant that their light no longer falls within the visible spectrum. By the time it arrives, it is shifted entirely into the infrared. That means no optical telescope, no matter how powerful, can truly see them. Hubble's deepest observations provided glimpses of young galaxies, but they were often obscured or incomplete. Webb, however, was designed with this very challenge in mind. Its massive gold-coated mirrors and ultra-sensitive infrared detectors are tuned to capture this stretched ancient light, transforming what was once invisible into vivid, detailed data. But it is not only distance that makes infrared essential, it is also the problem of dust. Galaxies, especially those undergoing mergers, are filled with thick clouds of gas and dust. In visible light, these clouds act like curtains, blocking the view of what lies behind them. But infrared light can penetrate dust, allowing Webb to reveal what's happening inside star-forming regions and the tangled centers of colliding galaxies. Thanks to this, astronomers can now see the hidden fireworks of early galaxy evolution: newborn stars igniting, black holes feeding, and galaxies tearing each other apart. The veil has been lifted, and the violent truth of the young universe is finally exposed. Consider the way Webb revealed tidal tales, the streams of stars flung outward during collisions. Hubble could detect these faint structures only in nearby galaxies, where they are bright and well-defined. But Webb's infrared sensitivity allows it to trace such delicate features across enormous distances, capturing them in galaxies from just a few 100 million years after the Big Bang. Suddenly, what had been invisible threads of matter appear woven through the cosmos, proof of early interactions on scales that defy previous models. Webb's precision also comes from its position. Stationed at the second Lagrange point, L2, about 1.5 million kilometers from Earth, the telescope avoids the interference of our planet's atmosphere. Earth's air absorbs much of the infrared spectrum, so ground-based telescopes can only capture a fraction of what Webb sees. Floating in the cold, dark vacuum of space, Webb can operate with unmatched sensitivity, cooled to extremely low temperatures to minimize its own infrared emissions. This environment allows it to detect signals so faint that they would otherwise be drowned out by noise. The combination of sensitivity, resolution, and infrared range has already delivered breathtaking results. Webb's deep field images, which peer into seemingly empty patches of sky, reveal thousands of galaxies layered across time, some of them so distant that their light began its journey when the universe was less than 1 billion years old. Within those galaxies, Webb has uncovered intricate details: spiral arms, starburst regions, and distorted shapes caused by gravitational interactions. These details prove beyond doubt that chaotic mergers were not rare but common, and that the early universe was alive with activity. One of the most dramatic demonstrations of Webb's precision came when it observed multi-galaxy collisions. Where older telescopes showed faint blobs, Webb revealed distinct galactic cores surrounded by luminous bridges of stars and gas. Astronomers could see not only that galaxies were colliding, but also the exact ways in which matter was being redistributed, fueling both star formation and black hole growth. For the first time, the choreography of galactic violence in the dawn of time was visible in sharp detail. Webb's infrared capabilities have also opened the door to studying the chemical fingerprints of early galaxies. By analyzing the spectra of light, scientists can determine the elements present in these systems. Remarkably, Webb has already detected heavy elements, carbon, oxygen, and even traces of metals far earlier than expected. This suggests that star formation and stellar death were happening much more rapidly than models predicted. The presence of these elements, hidden behind dust, but revealed by Webb's precision, further proves that the early universe was not primitive and simple, but chemically enriched and evolving at a staggering pace. The power of Webb lies not just in producing stunning images, but in delivering data that fundamentally challenge theory. Each faint arc of light, each distorted galactic core, each spectral line telling us of unexpected chemical complexity, is a piece of a puzzle that no longer fits neatly into the timeline we once trusted. The telescope has, in effect, given astronomers a new set of eyes, ones capable of seeing the true shape of the early universe: messy, violent, and accelerating far beyond prediction. And so, Webb's precision has done more than reveal chaos. It has forced cosmologists to confront their assumptions. If galaxies were already colliding so violently, black holes already growing so massive, and cosmic webs already stretching into place, then the theoretical models of galaxy evolution must be reworked. This is where the story turns toward the theorists, who are now racing to adjust their frameworks to accommodate the universe as it actually appears, not as they expected it to be. The flood of data coming from the James Webb Space Telescope has left theorists scrambling to rethink their models of galaxy evolution and cosmic structure. For decades, cosmology has been shaped by simulations rooted in the lambda cold dark matter model that combines the influence of cold dark matter with the accelerating expansion of the universe caused by dark energy. These models worked remarkably well in describing the broad strokes of cosmic history, from the distribution of galaxies to the formation of large-scale structures. But Webb's revelations of massive galaxies, frequent collisions, and supermassive black holes in the earliest billion years have exposed cracks in the theory. The universe is evolving far faster than simulations predicted, and theorists are now engaged in the challenging task of adjusting their models to account for this violent and accelerated early history. One of the first areas of revision concerns galaxy formation itself. Traditionally, simulations assumed that galaxies grew hierarchically. Small systems merged over long timescales to form larger and more complex structures. Webb has revealed that galaxies achieved significant mass and complexity far earlier than expected, forcing theorists to consider more efficient mechanisms for rapid growth. Some simulations are now experimenting with enhanced star formation efficiencies in the early universe, allowing gas to collapse and form stars at a rate far higher than in later epochs. This idea aligns with Webb's discovery of starburst galaxies, producing hundreds of stars per year within the first few 100 million years after the Big Bang. The challenge is to balance this accelerated growth with the constraints of physics, particularly the limits imposed by feedback processes like supernova explosions and black hole activity that can regulate star formation. Another area under revision is the role of black holes in shaping galaxies. The traditional view was that galaxies nurtured black holes, providing them with fuel over billions of years. But Webb's discovery of massive black holes so early has prompted a reversal of perspective. Perhaps black holes were the engines driving galaxy formation, not the byproducts. In this view, early galaxies and black holes co-evolved in a feedback loop. As galaxies collided in chaotic mergers, their central black holes merged as well, producing larger and more energetic black holes that influenced their environments. These black holes would have released enormous amounts of energy, heating gas, driving turbulence, and potentially triggering more star formation. New models now seek to incorporate black holes as active participants in galaxy growth from the very beginning, rather than as secondary features. Theorists are also reconsidering the role of dark matter in accelerating structure formation. Dark matter is thought to provide the gravitational scaffolding around which galaxies form. But Webb's observations suggest that this scaffolding assembled more quickly than expected. Simulations are being adjusted to explore scenarios where dark matter halos formed and clumped together at accelerated rates, creating dense regions where galaxies could collapse and merge rapidly. Some researchers are even questioning whether dark matter behaves in ways not yet accounted for in standard physics. Could dark matter interact with itself or with normal matter more strongly than we think? If so, it might have accelerated the early collapse of matter, helping to explain why galaxies and clusters appeared so quickly. These possibilities are controversial, but Webb's data has made them impossible to ignore. In addition to revising the behavior of dark matter, Some models are exploring changes in the physics of gas cooling and star formation. In the early universe, gas was pristine, composed almost entirely of hydrogen and helium. Without heavier elements to regulate cooling, gas clouds may have collapsed more efficiently than simulations predicted. This could have led to the formation of massive stars and star clusters much earlier than expected. These massive stars would have lived short, violent lives, exploding as supernovae and enriching their surroundings with heavy elements. Webb's detection of metals in early galaxies suggests this process was already well underway within the first billion years. Incorporating these rapid cycles of star birth and death into models may help explain how galaxies evolved so quickly. Another frontier in theoretical revision involves cosmic structure on large scales. Webb has revealed evidence of protoclusters and filaments of galaxies at times when the universe was thought to still be relatively unstructured. This suggests that the cosmic web, the vast network of filaments and voids that defines the large-scale shape of the universe, emerged far earlier than models predicted. To account for this, simulations are being updated to explore faster clustering of matter, potentially influenced by variations in the distribution of dark matter or the effects of early black holes and galaxies feeding energy back into their environments. Theorists are investigating whether feedback from black holes could have accelerated the clumping of gas and galaxies into large-scale structures, effectively jump-starting the cosmic web. Some theorists are even considering more radical revisions. If the lambda cold dark matter model cannot accommodate Webb's findings with modest adjustments, then entirely new physics may be required. Ideas such as warm dark matter, a version of dark matter that moves faster and clumps differently than cold dark matter, or modifications to the laws of gravity themselves have resurfaced as possible explanations. These ideas are controversial because lambda cold dark matter model has been extraordinarily successful in explaining a wide range of observations. Yet Webb's data suggests that something may be missing, and theorists must now explore whether small tweaks or paradigm-shifting changes will ultimately be needed. The implications extend beyond galaxy formation to the timeline of cosmic reionization. If galaxies were already massive and clustered so early, then reionization, the process by which the first stars and galaxies ionize the hydrogen gas filling the universe, may have occurred earlier and more rapidly than predicted. This has knock-on effects for the entire chronology of the early universe, forcing theorists to reconsider the sequence and pace of events. New models are being built to test whether reionization could have been completed in patches across the universe much sooner, driven by dense clusters of galaxies revealed by Webb. Theorists are responding to these challenges with a wave of new simulations designed to incorporate Webb's findings. These simulations are not simply repeating the old models with minor tweaks. They are attempting to recreate the violent, chaotic universe Webb has uncovered. By incorporating accelerated star formation, rapid black hole growth, and earlier clustering of dark matter, these models aim to reproduce the conditions of the first billion years. Already, some of these efforts are yielding insights that align more closely with Webb's data, but many mysteries remain unresolved. The tension between observation and theory is far from resolved, and it may ultimately drive one of the most significant revisions of cosmology in decades. As these new models take shape, one question looms especially large. What roles did the unseen forces of the universe, dark matter and dark energy, play in shaping this violent early history? Were they behaving differently in the dawn of time, influencing the growth of galaxies and structures in ways we have yet to understand? The more astronomers dig into the James Webb Space Telescope's revelations, the clearer it becomes that dark matter must be placed under the spotlight. For decades, it has served as the invisible backbone of cosmology, the gravitational framework upon which galaxies form and the cosmic web is spun. Without dark matter, the structures we see in the universe today could never have come together within the available time. But now, Webb is showing us that galaxies, clusters, and even supermassive black holes appeared far sooner than expected. This raises a provocative possibility. Perhaps dark matter was even more influential in the early universe than we thought, fueling a faster gravitational assembly that allowed galaxies to clump and merge at lightning speed. In the standard lambda cold dark matter model, dark matter is cold, meaning it moves relatively slowly compared to the speed of light. Its sluggishness is what makes it clump effectively, providing gravitational wells into which normal matter, gas and dust, can fall and ignite into stars and galaxies. This framework has worked beautifully in large-scale simulations, recreating the distribution of galaxies we observe today. But Webb's glimpse into the first billion years is exposing discrepancies. The observed galaxies are too massive, too structured, and too interconnected for the time available. If these systems assembled in such a short window, then dark matter halos must have formed faster, deeper, or more efficiently than our current models predict. One explanation is that the density of the early universe amplified dark matter's effects. When the cosmos was smaller and more compact, dark matter fluctuations, tiny differences in density left over from the Big Bang, may have collapsed into halos much more quickly. These halos would have been like invisible gravitational traps, pulling in ordinary matter at accelerated rates. Galaxies inside these halos could then grow rapidly, merging together far sooner than theory expected. Webb's observations of chaotic multi-galaxy mergers may be the direct consequence of these accelerated dark matter dynamics. In other words, the early universe was a place where dark matter's influence was not just important, but overwhelming, driving galaxies into traffic jams before they had time to evolve quietly. However, the speed of assembly revealed by Webb may require more than just density effects. Some theorists are now exploring whether dark matter itself might have properties beyond the cold, inert picture long assumed. For instance, what if dark matter could interact with itself through forces we have not yet detected? In such a scenario, called self-interacting dark matter, halos could collapse and merge differently, redistributing matter more efficiently and leading to the accelerated clumping Webb is revealing. Others speculate that dark matter may not be purely cold, but have a spectrum of behaviors, with a warm or fuzzy component that alters how structures form at small scales. Each of these possibilities represents a departure from the simple lambda cold dark matter picture, but Webb's discoveries are making them harder to ignore. Another intriguing angle is the potential connection between dark matter and black hole formation. Some scientists have suggested that concentrations of dark matter may have seeded the first black holes, or even formed black holes directly under certain conditions. If true, this could explain why Webb finds massive black holes so early in cosmic history. Dark matter halos could have acted not only as nurseries for galaxies, but also as incubators for the universe's most extreme objects. Such a link would tie together two of the greatest mysteries of modern astrophysics, the nature of dark matter and the origin of supermassive black holes. The role of dark matter may also help explain why Webb is finding interconnected cosmic structures so soon after the Big Bang. The filaments and clusters it reveals could have formed as dark matter halos, merged into larger structures with extraordinary speed, dragging galaxies along with them. Instead of the cosmic web gradually weaving itself together over billions of years, it may have been stitched rapidly by the invisible hand of dark matter. If so, then our models of how halos evolve and merge will need serious revision. The challenge now is to test these ideas. Webb's observations provide powerful evidence, but they must be matched with detailed simulations that incorporate new possibilities for dark matter. Already, theorists are experimenting with models that allow for faster halo growth, earlier clustering, and novel particle properties. The hope is that by adjusting the behavior of dark matter, simulations will finally reproduce the massive, chaotic galaxies Webb sees in the early universe. But if no adjustments work, it may mean something even more radical, that our understanding of dark matter is incomplete, or that it is not what we think it is at all. This re-examination of dark matter's role is not just a side note, it strikes at the core of cosmology. Dark matter makes up about 27% of the universe, dwarfing the 5% of normal matter that makes up stars, planets, and people. If its behavior is different than expected, then nearly a third of the cosmos needs to be reconsidered. This would ripple outward into every area of astrophysics, from galaxy evolution to the formation of cosmic structure to the very shape of the universe. And as we wrestle with these questions, another enigmatic force looms in the background: dark energy. If dark matter might have fueled faster growth, then what role did dark energy play in shaping the young cosmos? Could its influence have been different in the early universe, subtly altering the pace of expansion and evolution? The story of the early universe has always been told as one dominated by gravity, matter clumping together, galaxies forming, and black holes feeding. But lurking in the background of this cosmic narrative is something far more mysterious: dark energy. In our current cosmological model, dark energy makes up roughly 68% of the universe and is responsible for its accelerated expansion. It is the invisible force stretching space-time itself, counteracting gravity on the largest scales. Yet what James Webb has shown us about the rapid growth of galaxies and black holes in the early universe has raised an unsettling question. Could dark energy's role in the universe's earliest epochs have been different from what we see today? If so, then its fingerprints may be hidden in the unexpected pace of cosmic evolution Webb has uncovered. In the standard picture, dark energy becomes important only after the universe has expanded significantly. For the first few billion years, gravity was dominant, pulling matter into stars, galaxies, and clusters. Only after the universe grew large enough did dark energy switch on in a significant way, overpowering gravity and accelerating expansion. This late-time acceleration is supported by observations of distant supernovae, the cosmic microwave background, and large-scale galaxy surveys. But if galaxies and supermassive black holes were already forming and colliding at speeds that defy our models, it may be worth asking whether dark energy was truly as passive in the early universe as theory assumes. One speculation is that dark energy may not be a fixed, unchanging property of space-time, but something that evolves with time. This idea, known as dynamic dark energy or quintessence, suggests that dark energy could have been weaker or stronger in the universe's early days. If it was weaker, then gravity would have had more room to dominate, allowing matter to clump together faster and fueling the accelerated assembly Webb observes. On the other hand, if dark energy had a different form early on, perhaps even behaving as an attractive force rather than a repulsive one, it might have actively contributed to early structure formation, before later flipping to its role as the driver of cosmic acceleration. There are even more exotic possibilities. Some physicists propose that what we call dark energy may not be a single, simple phenomenon, but the result of deeper physical laws not yet uncovered. For instance, it may be tied to scalar fields, quantum fields permeating all of space, whose energy density changes over time. In the early universe, such fields could have behaved very differently, influencing the collapse of matter and the growth of galaxies in ways that standard lambda cold dark matter model does not account for. These fields could even have interacted with dark matter, amplifying gravitational effects in the young cosmos. Webb's findings may be hinting at such an interplay, since the combination of accelerated galaxy growth, early clustering, and massive black holes seems to require forces beyond what we currently model. Another hypothesis is that dark energy might have had regional variations in the early universe. Instead of being perfectly uniform, its density could have fluctuated from place to place, creating pockets where expansion was slower and matter could clump more effectively. In such regions, galaxies would have had more time to grow and merge before the repulsive push of dark energy caught up. If Webb is detecting galaxies from these privileged regions, it might explain why so many appear more massive and mature than the average models predict. Testing this would require detailed statistical surveys of early galaxies, something Webb is well suited to continue providing. The potential role of dark energy also ties into the broader question of whether the cosmic timeline itself is skewed. If expansion was not as uniform as we think, then our interpretation of redshift, the stretching of light as the universe expands, could be subtly off. Redshift is the ruler by which astronomers measure cosmic time and distance. If dark energy behaved differently in the early universe, it could alter the mapping between redshift and age, effectively reshaping the timeline we assign to Webb's discoveries. In other words, galaxies we think are impossibly massive for their epoch might actually be slightly older than we calculate, not because they formed faster, but because our cosmic clock is miscalibrated by assumptions about dark energy. Of course, these speculations remain highly theoretical, and dark energy is notoriously difficult to study. Unlike dark matter, which interacts gravitationally with visible matter, dark energy does not clump or leave direct traces in galaxy dynamics. Its effects are only apparent on the largest scales, through the way it alters expansion. That makes Webb's discoveries especially tantalizing, because they provide indirect evidence that our understanding of cosmic forces at play in the early universe is incomplete. If dark energy's influence was different back then, it might finally offer a clue about its true nature, something that has eluded scientists for decades. One area where this speculation becomes especially important is in understanding the transition from deceleration to acceleration. According to the Standard Model, the universe's expansion was initially slowing under gravity, only to begin accelerating around 5 billion years ago due to dark energy. But if early galaxies formed too quickly, perhaps the balance between gravity and dark energy tipped differently in the first billion years. Could it be that dark energy's strength was delayed, giving gravity extra time to dominate and assemble massive structures? Or conversely, could dark energy have accelerated matter inflow into dense regions before settling into its modern repulsive role? These possibilities sound radical, but Webb's data is forcing cosmologists to explore them seriously. The possibility that dark energy evolves over time also resonates with the concept of the early dark energy hypothesis. This idea, which has gained attention in recent years, suggests that a small but significant amount of dark energy may have been present during the early universe, altering its expansion rate and structure formation. Early dark energy models were initially proposed to address discrepancies in measurements of the Hubble constant, the rate of cosmic expansion. Now, Webb's findings may give them new relevance. If galaxies were forming faster because expansion was slightly different at the dawn of time, early dark energy could provide part of the explanation. What makes this line of inquiry so compelling is its potential to unify multiple cosmic puzzles. Dark energy's role may help explain not just Webb's shocking discoveries of early galaxy growth, but also long-standing tensions in cosmology, like the mismatch between local and cosmic measurements of the Hubble constant. If dark energy behaved differently in the past, it could ripple through all of these problems, reshaping our entire understanding of cosmic history. Still, any attempt to revise dark energy's role must confront a sobering reality. we know almost nothing about what dark energy truly is. It could be a property of the vacuum, a quantum field, or even an illusion created by modifications to gravity itself. Webb has not solved this mystery, but by revealing a universe that grew too fast, it has given us reason to consider whether dark energy's effects were more complex than we ever imagined. And that is what makes this chapter of the story so consequential. If dark matter accelerated structure formation and dark energy influenced growth differently in the past, then the entire framework of cosmic history may need revision. This isn't about minor tweaks or adding new details. It's about rethinking the laws that govern the evolution of everything. Which brings us to the next point: why these discoveries change everything we thought we knew about the cosmos, rewriting the story of how galaxies, stars, and black holes came to be. The revelations brought forth by the James Webb Space Telescope are not mere refinements of our cosmic story. They are tectonic shifts that force us to reconsider everything we thought we understood about the history of the universe. For decades, cosmology has been guided by a broadly accepted narrative. The Big Bang occurred 13.8 billion years ago, followed by hundreds of millions of years of relative simplicity. Then, gradually, galaxies began to form. Black holes grew slowly, stars enriched their surroundings, and cosmic structure unfolded at a measured pace. This framework was elegant, logical, and reinforced by countless observations and simulations. But Webb's discoveries have ripped holes in this picture. What it has revealed are galaxies, clusters, and supermassive black holes appearing far too soon, growing far too large, and merging far too violently for our models to explain. This isn't a case of needing to tweak the timeline slightly. It's a challenge to the very foundations of how we think the universe works. The first reason this changes everything is the speed of cosmic growth. We once believed that time was the central ingredient of the universe's evolution, that the complexity we see today was only possible because billions of years had passed. Yet Webb has shown us galaxies that look surprisingly mature less than 1 billion years after the Big Bang. These galaxies are not just faint blobs of light. They have structure, mass, and luminosity that rival galaxies billions of years older. This forces us to abandon the idea that time alone governs growth. Something else, whether it be more efficient star formation, accelerated dark matter clustering, or unknown physics, was pushing the universe to mature faster than theory allows. The comforting image of a patient, orderly cosmos gives way to one of urgency and chaos. The second transformative insight is the role of black holes. For decades, astrophysicists believed black holes were passengers in the cosmic story, forming only after galaxies had provided them with the necessary conditions to grow. Webb has turned that view on its head. By detecting quasars and black holes billions of solar masses in size, at times when galaxies themselves should have been tiny, Webb suggests that black holes may have been the drivers of galactic evolution, not the byproducts. This flips the cause and effect relationship we've long assumed. Instead of galaxies nurturing black holes, perhaps black holes sculpted galaxies from the very beginning, using their gravitational pull and energetic feedback to shape their environments. If true, it means our models of galaxy growth are not just incomplete, they are fundamentally backward. Another reason this changes everything is the early assembly of cosmic structure. The cosmic web, the vast network of filaments and voids, was thought to be the culmination of billions of years of matter coalescing under gravity. Yet Webb has revealed filaments and protoclusters already in place within the universe's first billion years. This means that the scaffolding of the cosmos, the very backbone upon which galaxies are strung, was constructed far earlier than our models allow. It is as if a building's steel framework appeared almost instantly, leaving us to wonder what force accelerated its construction? If dark matter halos assembled faster, or if cosmic expansion unfolded differently due to dark energy, then our entire framework of structure formation must be revised. We must also confront the implications for the timeline of cosmic history. Every redshift measurement Webb provides is a window into the past, and what it shows us is a universe that looks too old for its age. The galaxies Webb sees at high redshift are not primitive, they are advanced. This raises questions about whether our cosmic clock is miscalibrated. If our understanding of how expansion relates to time is off, perhaps due to evolving dark energy, as some speculate, then we may be placing these galaxies in the wrong part of the timeline. But even if the clock is correct, then we are forced to accept that the universe is capable of building itself much faster than we imagined. Either possibility represents a seismic shift in cosmology. The shockwaves extend into the realm of stellar and chemical evolution. Heavy elements like carbon, oxygen, and iron are forged in stars and spread into space through supernova explosions. For these elements to appear in the universe, generations of stars must live and die. According to our models, this process should take billions of years to enrich galaxies to significant levels. And yet, Webb has already detected signatures of heavy elements in galaxies less than 1 billion years old. This suggests that stars were not just forming quickly, they were cycling through their lifetimes at astonishing rates, enriching their environments far earlier than expected. The timeline of chemical evolution, like that of galaxy and black hole growth, appears to be compressed, forcing us to rethink how stars lived and died in the universe's infancy. What makes all of this so profound is that the discrepancies are not small. These are not minor outliers that can be patched with small adjustments to theory. The galaxies Webb is revealing are orders of magnitude more massive than expected. The black holes are billions of solar masses too heavy, too soon. The clusters and filaments are billions of years ahead of schedule. Each discovery is a glaring contradiction, and together they form a chorus demanding a new theory of cosmic history. If Webb had revealed just one such anomaly, it might have been dismissed as an oddity. But it is finding them everywhere it looks. This suggests that the violent, fast-paced early universe is not an exception, it is the rule. In light of this, some scientists argue that cosmology is on the verge of a paradigm shift. The lambda cold dark matter model has been the reigning framework for decades, explaining everything from the cosmic microwave background to galaxy distribution. But Webb's data has forced us to consider whether lambda cold dark matter model is incomplete. Does dark matter behave differently than we thought? Is dark energy evolving in time? Are there new forces or particles that shaped the early universe? Or is our interpretation of expansion itself flawed? These are not minor questions. They strike at the heart of physics, requiring us to rethink gravity, quantum fields, and the very structure of space-time. This is why Webb's findings change everything. They don't just add new details to the story of the universe, they rewrite the story entirely. Instead of a calm, gradual emergence of complexity, we see a universe that was restless from the start, exploding into galaxies, black holes, and structures almost as soon as it began. The cosmos, once thought to be patient and orderly, now appears impulsive and unruly. This isn't just an adjustment to theory, it's an invitation to rebuild cosmology from the ground up. And with every new image Webb sends back, the puzzle only grows. Each observation adds another piece that doesn't quite fit, deepening the mystery of how the universe grew so fast, so violently, and so soon. Which leads us to an important realization. The story is far from complete. The mystery continues, and the more Webb reveals, the more questions it raises about the very foundations of our cosmic understanding. The James Webb Space Telescope has already upended so much of what we thought we knew, but its journey is far from over. In many ways, what we've seen so far may only be the beginning. Webb is still in the process of surveying the deepest reaches of the cosmos, and with every new image it sends back, the mystery deepens. Each observation peels back another layer of time, revealing galaxies and structures even closer to the Big Bang than the ones we've already studied. And if history is any guide, those observations are unlikely to confirm our expectations. They are more likely to challenge them. The sense among astronomers is that stranger, even more inexplicable discoveries lie just beyond the horizon. Already, Webb has shown us galactic collisions happening earlier than anyone imagined possible. But the telescope's capabilities extend to redshifts so extreme that we are effectively looking at the very first few 100 million years of cosmic history. This is the era where galaxies were just beginning to form, where stars were igniting for the first time, and where the seeds of supermassive black holes may have been planted. If Webb continues to reveal massive galaxies and violent mergers at these epochs, it would push the problem even further back, leaving us with almost no time at all for the cosmos to have assembled such complexity. We would then be forced to consider whether our entire timeline of the early universe is fundamentally misaligned, or whether there are processes at play we've not even begun to imagine. One of the most tantalizing prospects is the discovery of earlier cosmic crashes. So far, Webb has revealed multi-galaxy mergers less than 1 billion years after the Big Bang. But what if such events were happening at 300 or 400 million years? At that point, the universe was barely out of infancy. The presence of large interacting galaxies so soon would be profoundly unsettling, suggesting that cosmic structures sprang into existence almost instantly after the Big Bang. Such a finding would not just stretch our models, it would tear them apart. And yet, given what Webb has already uncovered, astronomers are preparing themselves for exactly that kind of surprise. Beyond galaxy collisions, Webb is also poised to deepen the puzzle of early black holes. Already, the telescope has found supermassive black holes in places where they should not exist. But with deeper surveys, it could reveal even earlier quasars, brilliant, blazing galaxies powered by black holes billions of times the Sun's mass. If such objects are discovered within just a few 100 million years of the Big Bang, the question of how they formed will become even more urgent. Did they arise from exotic processes like direct collapse, or do we need to invoke entirely new physics to explain their rapid growth? Each new detection adds pressure on theorists to revise models, and Webb is only just beginning to scratch the surface of what it can reveal. Even the cosmic web itself, the vast scaffolding of filaments connecting galaxies, may be exposed in earlier detail than ever before. Webb has already found hints of protoclusters and filaments forming at unexpectedly high redshifts. With time, it may reveal that these structures were in place almost from the very start, challenging our ideas about how matter aggregated under the influence of dark matter and gravity. If filaments and clusters existed at redshifts corresponding to just a few 100 million years post-Big Bang, it would imply that the universe's skeleton was drawn nearly as soon as it was born. That possibility radically redefines the timeline of cosmic structure formation. The excitement around Webb lies not just in what it has already revealed, but in its open-ended potential. The telescope is designed to operate for many years, possibly decades, continuously collecting light from the most ancient corners of the universe. Every deep field survey adds thousands of galaxies to our catalogue, and with each one comes the chance for another anomaly, another galaxy too big, too bright, or too complex for its age. Already, the scientific community is revising papers, running new simulations, and scrambling to keep pace with the torrent of data. But the truth is that Webb may always remain ahead of us, uncovering mysteries faster than we can solve them. This state of uncertainty is not a frustration. It is the essence of science. For the first time, we are not just glimpsing, but truly witnessing the dawn of time with clarity. And what we see is not a universe that matches our theories neatly, but one that defies them at every turn. It is a reminder that the cosmos still holds secrets we have not yet imagined, that our models are provisional, and that discovery always outruns certainty. So the mystery continues, and it will continue as long as Webb stares into the void. Each new image may reveal another piece of the puzzle, a galaxy too massive, a black hole too early, a merger too violent. We are, in real time, watching the story of cosmic history being rewritten, frame by frame. And this ongoing revelation sets the stage for one last reflection. If the early universe was this chaotic, this violent, and this creative, then the story of our cosmic origins must be told not as a calm unfolding, but as a violent birth of the cosmos, where collisions and chaos were not accidents, but the very engines of creation. The James Webb Space Telescope has given us something profound, an entirely new vision of the cosmos. For decades, we imagined the early universe as a place of fragile beginnings, a calm nursery where the first stars flickered on and galaxies grew slowly, patiently, like seedlings rising in an endless field of space. But Webb has torn down that comforting picture and shown us something far more raw, far more violent, and far more extraordinary. The early universe was not quiet. It was not gentle. It was a storm of collisions, chaos, and relentless creation. It was a crucible where galaxies smashed together in crowded neighborhoods, where black holes collided and grew at impossible speeds, and where the scaffolding of the cosmic web emerged with astonishing rapidity. What we see in Webb's data is a universe impatient with itself, racing headlong into complexity almost as soon as it was born. This realization changes not only our scientific understanding, but also our sense of place in the cosmos. Every star, every planet, every atom of carbon in our bodies was forged in the aftermath of that violent birth. The collisions Webb has captured are not distant curiosities. They are the ancestral battles that set the stage for everything we know. The galaxies that merged in chaos eventually became the grand spirals and ellipticals we see today. The black holes that grew too fast shaped the galaxies around them, regulating star formation and carving the environments that allowed solar systems like ours to form. Even the cosmic web, stitched together so quickly, became the framework upon which all of cosmic history unfolded. In a very real sense, the chaos of the early universe is written into us. We are the children of that violence. And what a violence it was! Imagine galaxies the size of the Milky Way colliding only a few 100 million years after the Big Bang, when the universe was still in its infancy. Imagine supermassive black holes, already billions of times the mass of the Sun, devouring gas and merging in titanic collisions that shook space-time itself. Imagine newborn stars igniting by the thousands in furious bursts, their light cutting through the darkness of the cosmic dawn, only to explode in supernovae that enriched their galaxies with the elements necessary for life. This was not a tranquil unfolding, but a cosmic storm, a symphony of destruction and creation that sculpted the universe into what it is today. The violence of the early cosmos also serves as a reminder of the limits of human certainty. For decades, our models told us that galaxies needed billions of years to mature, that black holes required eons to grow, and that the cosmic web was a slow, deliberate construction. Webb has proven otherwise. It has shown us a universe that defies those assumptions, forcing us to confront the possibility that we do not yet understand the laws that govern cosmic evolution. Perhaps dark matter behaves differently than we think. Perhaps dark energy is not constant, but changes with time. Perhaps the physics of the early universe included processes we have not yet discovered. Whatever the explanation, one thing is clear. The cosmos is stranger, faster, and more dynamic than we ever dared to imagine. But this strangeness is not unsettling. It is awe-inspiring. The universe is not bound by our expectations. It writes its own story, and Webb has given us a chance to read it in greater detail than ever before. The galaxies Webb has revealed are not anomalies. They are chapters in a cosmic epic we are only beginning to understand. Each collision, each merger, each impossibly massive black hole is a reminder that creation and destruction are not opposites in the universe. They are partners. Out of chaos comes structure. Out of violence comes beauty. Out of collisions comes the possibility of life. And so, as we reflect on Webb's discoveries, we are left with a vision of the cosmos not as a peaceful garden, but as a living storm. The early universe was a furnace of activity, a place where matter was pulled, torn, and reshaped into ever more complex forms. It was a place of relentless motion, where the laws of physics pushed galaxies and stars into existence with breathtaking urgency. It was, in every sense, a violent birth, but one that gave rise to all the wonder we see today. This closing reflection is not the end of the story, because the story itself is still unfolding. Webb continues to send back data, and with each new image comes the possibility of an even greater shock. Galaxies larger, black holes earlier, structures more complex than we ever thought possible. The mystery continues, and with it, the promise that our understanding of the universe will never be static. What Webb has taught us is that the cosmos is not only more magnificent than we imagined, it is more magnificent than we can imagine. In the end, the lesson of Webb's revelations is both humbling and inspiring. The universe is not a quiet place, patiently waiting for us to uncover its secrets. It is a place of fire, motion, and relentless change, where creation is inseparable from destruction, and where every beginning is born from chaos. The galaxies that Webb sees colliding in the dawn of time are not distant strangers. They are our ancestors. The light Webb has captured is the light of our own beginnings. And it tells us a story not of calm, but of storm. A story of the violent birth of the cosmos, the storm from which everything we see today, including ourselves, has come to be. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.